Given the head of a singly linked list and an integer k, rotate the list to the right by k places, the tail should advance k steps forward and wrap around to the front. Return the head of the list after rotation. Example, values 1 through 5 with k equal to 2. The last two nodes, 4 and 5, move to the front, so the new order reads 4, 5, 1, 2, 3. Picture 5 nodes in a row and k equals 102. Each rotation sends the tail around to the front, so huge K repeats the same wrap many times. 102 modulo 5 is 2, only 2 effective rotations matter. The real first step is measuring the length n, then replacing k with k mod n so we ignore full laps. Normally the tail's next pointer is null. After we know n and the effective k, we point the tail back at the head. That closes the chain into a ring. Now rotating is not about moving every cell, it is choosing a new starting line on the ring. Walk forward from the head along the ring. For a right rotation by the effective k, take n minus that k minus 1 steps, you land on the new tail, the back of the new line. Here n is 5 and k mod n is 2, so 5 minus 2 minus 1 equals 2 steps, first to node 2, then to node 3, that is the new tail. The new head is the node right after the new tail. Set the new tail's next pointer to null so the ring snaps open. The piece that used to follow the new tail becomes the front of an ordinary list again, 4, 5, 1, 2, 3. Place a scout on the head and call it old tail for now. Walk it forward until it sits on the last node, the place where next would be null. While you move, count nodes so L becomes the length. You need L to shrink huge K with modulo, and you need the real tail to close the chain into a ring. The scout now rests on the last node. Set that node's next to the head, the trailing null goes away and a wrap link appears. The structure is now one continuous loop. There is no separate start or end until we cut it open again. Reduce k with the length, replace k by k mod L, 12 modulo 5 is 2. Only that remainder drives the rotation. Afterward, the new tail sits L minus k minus 1 forward edges from the head, here 5 minus 2 minus 1 equals 2 hops along the ring. Bring in a second pointer called new tail, starting at the head. Hop it forward exactly L minus k minus 1 times, in this example 2 hops, landing on node 3. That node is the pivot, everything after it will become the new front of the straight list. The answer head is new tails next, node 4 here. Set new tails next to null to break the ring, remove the wrap, and lay the values out as 4, 5, 1, 2, 3 with null at the end. Return that new head pointer. Let n be the number of nodes. Time is big O of n, one pass finds the length and the true tail, we close the ring in constant time, reduce k with modulo in constant time, walk at most n steps to the new tail, then break the ring in constant time. Each node is involved only a constant number of times across those phases, so overall work is linear in n, extra space is big O of 1, only a few pointers like the tail walker, new tail, and new head, with no auxiliary list. The pseudocode walks from the head to find the length L and the last node, points that tail back at the head to form a ring, replaces k with k modulo L, handles the zero case by reopening the ring, then walks L minus k minus 1 steps from the head to find the new tail, breaks the link after it so the new head leads a normal list again, and returns that new head.